have the pleasure of having Professor Michele Cicoli visiting from the University of Bologna. So he's one of the world experts in string cosmology. So the theme here is basically string theory applied to different aspects of high energy physics, particularly cosmology and black holes. So he's written one of the recent comprehensive reviews on string cosmology. He's also very famous for a paper on fiber inflation. He's also one of the principals, builders of string models for phenomenological purposes. He came on a 25-hour flight. I think it's actually 28 hours because of delays. So we're very lucky to have him. And we're very grateful for his sacrifice to come at very short notice. Okay, so we asked him at very short notice and he agreed to come. We're also very privileged to have Professor Sen. He will give a lecture later. So he's also with us today. Feel free to ask questions, but please keep your questions short. Okay. And if you you can always ask questions after the lecture. Okay. So we want him to give you all the material that you need so that you can make your way into research. Okay. Okay. And thank you so much. I'm hand over to yeah. Professor Cicoli.
Well, thank you very much, Mahbub, for the introduction and for the invitation. So I couldn't say no because also, Hamed was my master's student at the University of Bologna. And so it's the first time for me here in Bangladesh. I'm very happy to be here. And they also told me that there should be another lecturer, Fernando Quevedo, giving lectures on string cosmology. And I had already talked to him and I had to give 4 lectures on string compactifications and then 3 lectures he had to give on more model building in string cosmology. But I heard just yesterday that unfortunately he had to cancel, which means that the introduction will be shorter so that I can devote at least 2 lectures on actual model building in string cosmology. So the plan is that the first 2 lectures today will be whiteboard lectures. The first one, I will try to give you an idea of what a string compactification is. So the second one will be about how to stabilize the moduli, which are scalar fields that arise in 4 dimensions once you compactify string theory. And these are crucial fields for cosmological applications. And then tomorrow I have prepared actually 2 talks with slides. So the first one, I will present at least one model in full detail where you can do inflation in string theory. And the second lecture tomorrow will be about axioms from string theory and their applications mainly in dark energy. So to explain the acceleration of the universe today, not in the early universe as inflation. So that's my email address, michele.cicoli@unibo, University of Bologna.it. So if you want to ask questions, not just after the lectures, but when I'm back home, send me an email, no problem. So let's get started. Let me say that, this is a huge research area, and I have only a few hours, so I cannot give you all the details. I also don't know what is the level of your preparation. I know that there's been a preschool, and you should be familiar with some string theory, with some supersymmetry, I guess some cosmology, general relativity, and so maybe some differential forms, complex geometry. Have you heard of it a bit? Okay, very good. So in these lectures, I will mainly try to describe things. So I won't be able to go into details. But for example, if you want to know more details after the lectures, you can ask me and we can go through them together. So don't worry if you don't understand everything. That's normal. So the idea, I guess, is that you get the main picture behind this research field. So you've seen that I'm not used to whiteboards. I'm always using blackboards, but let's see. So you've seen that string theory is a consistent theory of quantum gravity. Quantum gravity because there is a graviton in the spectrum, and consistent, you've seen probably that the Fock space is well defined once you have Weyl invariance. So that fixes the critical dimension, which is 26 for the bosonic string and 10 for the superstring. And in the superstring, there is also the GSO projection that removes the tachyon. So the theory is consistent, but lives in 10 dimensions. I think you've seen this, right? So let me say that superstring theory. So let's consider the situation with fermions lives in 10 dimensions. It's not a bad number. So it's one of the few theories that predicts the number of space-time dimensions. But however, this is different from the one we see or we seem to see at the moment in nature, right? Which is 3 space plus 1 time. And so let's say, but we see only 4 dimensions. This means that if you want to make contact of string theory with the real world, 6 dimensions should be compact, right? Should be small, and the radius associated to these extra dimensions should be smaller than the present accuracy with which we can test nature. So we need to study string compactifications, where I have that R19, so 10-dimensional Minkowski, now is some 10-dimensional manifold X and D, which is what we see, R13, so Minkowski, 4-dimensional Minkowski, times some compact 6-dimensional space, Y6, and with 1 over the volume of Y6D, right? So this is a 6-dimensional manifold. So if I take 1/6, now I get 1 over a length, which is an energy. Now, this one is called MKK. KK is for Kaluza-Klein. Have you seen something about Kaluza-Klein theories? Yes, you did? Okay, very good. And so now these, in order to explain why we haven't seen the extra dimensions yet, should be much bigger than what? KK is Kaluza-Klein. Yeah, I'm asking, so the Kaluza-Klein scale should be bigger than the largest energy that we can at the moment test experimentally, right? Because the inverse would give the smallest length that we can test at the moment. And this is what? For example, the energy that is there at the LHC. And this is around, say, 1, roughly speaking, TeV. Okay? So as long as these extra dimensions have the volume to the minus 1/6, which is much bigger than the energy of the LHC, that's fine. There's nothing wrong with that. It means that the extra dimensions are so small that we haven't seen them yet. So the idea then is the following. So let me draw a picture with energies. So somewhere up here, there is the Planck scale, okay? The scale where gravity becomes strongly coupled, so the scale of quantum gravity. So you know that M Planck is around 10 to the 18 GeV. And somewhere here, one has the string scale, M string, MS. Okay, so this one is, so the string scale is basically the inverse of the string length, 1 over the string length, and the string length is 2 pi square root of alpha prime. You've seen this. And let's say that we are at energies above M string. So then we see the whole, at least let's consider perturbative string theory. So we see the whole 10-dimensional string theory with all the string states, right? And for this talk, this set of lectures, we will consider the superstring theory, which is best understood in terms of cosmological applications, which is type 2b. I will try to explain why. So then what you do, you go, for example, at energies which are below the string scale. So that means that you don't have enough energy to produce the massive string states. So you only see the massless string modes. So here you are basically considering a 10-dimensional field theory. And this theory is a theory that is supersymmetric. It includes the graviton. So it's a theory of supergravity in 10 dimensions. So this is only considering the massless string modes. So considering only the massless string modes. And then somewhere down here, now we make contact with what I said earlier on. Now I go basically, first of all, at distances which are larger than the size of a string. So I see the string as a point-like particle, but still I see here the extra dimensions. But if I now, let's say that here there is mkk, if I now take a further low energy limit and I go below mkk, I get a 4-dimensional effective theorem, which is again a supergravity theorem whose field content is given by the original string theory you start off with. Yes, so when I say effective field theory, it means a theory that is valid effectively below some energy scale. So in this case, the energy scale associated to that is the Clauser-Klein scale. Yep. So let's try to relate these scales one to the other. So, for example, if you start from 10 dimensions, and so the supergravity action in 10 dimensions contains a term like this, m string, roughly speaking, to the 8th. Then you have the integral over d10x, right? You have a 10-dimensional action. Then you have square root of minus the determinant of the metric in 10d. Then you have e to the minus 2 phi, where phi is the dilaton. You've seen that this is one of the massless modes in the string spectrum, times the Ricci scalar in 10d. It's a kind of generalization of the Einstein-Hilbert action in 10d. Now, when you go down to 10d to 4d, by considering that your space-time looks like this, okay, R13 times some y16, then you have that. So you dimensionally reduce. So it's called dimensional reduction. So you go from 10d to 4d. So what happens is that this will become m string to the 8th. Now here the integral over d10x becomes the product of two integrals. right? One over d4x and the other over d6y. Let's call it y. So this will be some integral over d6y square root of minus g 6d. So this at least will contain a term like this. So now there is also the integral over d4x e to the minus 2 phi. Then you have the square root of minus g for d. And then there is a piece with the Ricci in for d. Okay. The reason why I'm doing this because I want to see how m Planck is related to m string, and then how in turn it's related to mkk. So I want to see how these scales are related to each other. Now, let's consider the situation where phi is in the vacuum. Okay, so this gets just the vacuum expectation value as a constant. Now, this quantity here will give you what? You're just integrating over all your y6d here. This is the volume. Very good. So this will be the volume of y6d. Very good. And so let me put this in the vacuum. Sorry, phi. This will be the vacuum expectation value phi. So then I can write this down as m string to the eighth times the volume of y6d times e to the minus 2 vacuum expectation value phi, which I bring out of the integral. And then you have the integral over d4x square root of minus g for d times r for d. So then you see that here, ignore the prefactor, here you have to obtain the Einstein-Hilbert action, right? So you know that in 4D, what multiplies the Einstein-Hilbert action is a mass scale squared, which is exactly the mass scale associated to four-dimensional gravity, which is m Planck squared. So that's the relation that you can use to read off the dependence of m string on m Planck and vice versa. So a nice way to do that, maybe I should not come down here. Maybe let me go here. So, for example, we can try to measure the volume in the natural units of the theory, which is the string scale. So, if we write the volume as, so the volume of y6d, we can write it down as some dimensionless quantity, let me call it curly v, times the string length to the sixth, right? Because this is a six-dimensional space, which I can write as the volume times m string to the minus 6 because of the previous relation. So then you have that this quantity here, as I said earlier, should scale as m Planck squared, right? So then you find that m string squared times this dimensionless volume in string units times e to the minus 2 phi. And basically one has that e to the vacuum expectation value phi by studying string amplitudes. One can realize that this is the string coupling, so G string. So that's the string coupling, which you see comes out as the vacuum expectation value of a field. So it is in principle not a free parameter. So it's something that in an effective field theory, one can predict if you know what is the vacuum expectation value phi. For example, if phi has got a potential and the minimum, you can try to work it out. So here you will get that this is divided by G string squared because of that. G string squared. So this goes like m Planck squared. So that's the relation between these two quantities. So if I come back here, So I find that M string here is G string times M Planck divided by square root of the volume. So the fundamental quantity should be the string scale from the point of view of string theory, and M Planck somehow is a derived quantity, but we know what M Planck is. So we can trade, if you want, M string for M Planck, and we can try to write down everything in terms of units which are given by M Planck. Now, if we keep doing this, let's see MKK, we've seen that this one is given by, we've seen it there, so it's 1 over the volume to the 1/6. So this would be M string divided by my dimensionless volume to the 1/6. I can then write down M string in terms of M Planck, as I did there. So this becomes G string times M Planck divided by volume to the 2/3. It's a simple thing, just substitute that relation. So now you see that if we are in a regime where we trust perturbation theory, so the regime where you trust perturbation theory is when G string is small. And on top of that, actually, there are different kinds of perturbative corrections in string theory. So you don't have just G string corrections, which are loop corrections to your effective action. There are also curvature corrections associated with the fact that the string can propagate on a curved background, which from the point of view of the effective theory, these are higher derivative corrections, and these are controlled by the volume. So you trust your effective theory basically. Let me write it down here. So you trust the effective theory. I will comment on this a bit more later. If, let's say, if G string is small, which is something that somehow at the beginning you assume to be able to write down an effective theory. So assuming that G string is small, but then given that it is given by the vacuum expectation value of a field, in your effective theory, you should find that this has got a potential where indeed G string is small. Okay, and on top of that, the volume, dimensionless volume, should be big. Let's say much bigger than 1. Now, if we are in this limit where you trust perturbation theory and higher derivative corrections are small, what happens is that you see the string scale is smaller than the Planck scale because of the string and 1 over square root of the volume. And the Kaluza-Klein scale is M Planck divided by the volume to the 2/3. Here there is volume to the 1/2. So this is even smaller. So that's why I drew it like that. So that's the idea. And so in this limit, one is that MKK is below M string, which is below M Planck. Now, how small is M string? How small is MKK? Well, we don't know what is the value of the string. We don't know what is the value of the volume, which is also a field, by the way. We will see in the 4-dimensional effective theory. But at least we know that the Kaluza-Klein scale, as we've seen, cannot be smaller than 1 TeV. Okay, that sets bound on G string and the volume. Now, if we start from type 2b, so this is a theory that has got 2 supersymmetries. Okay, so that's a theory that will give rise to a 10-dimensional effective theory that has got n equals 2 supersymmetry in 10 dimensions, which does not mean n equals 2 supersymmetries in 4 dimensions. Okay. So the number of supersymmetries, I will also try to explain this if I have time, that we see in 4 dimensions depends on this guy, on the topological properties of the compact space. So if the compact space is the simplest thing that one can write down, for example, a 6-dimensional torus, then what happens is that each supersymmetry in 10 dimensions gives rise to 4 supersymmetries in 4 dimensions. So in this case, one would have that one gets n equals 8 supergravity, let's say if y6, for example, is a 6-dimensional torus. Okay. Now, what we see in nature at the moment is no supersymmetry. So what we see in nature is n equals 0. Okay, so far. But so this means somehow that one should try to break this number of supersymmetries down to n equals 0 to make contact with what we see in nature. And there are different strategies to do that. Of course, one can also start from a different superstring theory. So instead of type 2b, for example, one can start from the heterotic string. So in the case of the heterotic string, one would have n equals 1 here instead of n equals 2. And the theory compactified on a T6 will have n equals 4, for example, in 4 dimensions, which looks a bit better. But we will see that, for example, if instead y6 is a Calabi-Yau, we will see what is a Calabi-Yau threefold, 3. This breaks the number of supersymmetries by 1/4. Okay, so then you will go down to n equals 2, just by choosing a different compactification manifold. And then there is an operation which is called orientifold projection, that it's a projection that flips the orientation of the string. That's why it is called orientifold, on top of an involution on the Calabi-Yau. And that basically projects out half of the states, and the theory is n equals 1 after orientifolding. So let's say orientifold projection. Maybe for most of you, a lot of these are just words at the moment, but at least I think it's important to have the picture in mind at the beginning. Okay.
Can you please elaborate what do you mean by sort of the n is equals to 2 and the 4 is supergravity n is equal to 8 to a is equal to 2?
Right. So you've seen you see some supersymmetry. Not that much. So for example, in supersymmetry, you've seen that it is just an extension of the Poincaré group, right? So in the Poincaré group, you have only bosonic generators, the standard ones for Lorentz, plus space-time translations. Now, on top of that, you can add fermionic generators. And so these are generators like Q alpha, where this alpha is a spinorial index. So alpha is 1, 2, because these are Weil spinors. So this is a left-handed Weil spinor. And that comes along with some right-handed conjugate spinor. Maybe you've seen this notation alpha and alpha dot. Very good. And then you need to extend the Poincaré algebra to become the super Poincare algebra. There are transformations generated by these guys. For example, there are now one has to add to the commutation relations also some anti-commutation relations, for example, between these guys. So you have some Q alpha, Q bar alpha dot, for example. Sorry, this is an anti-commutation relation. This is something like 2 sigma mu with the Pauli matrices, right? So sigma mu is the identity sigma. And this has got indices alpha alpha dot p mu. So the four momentum, the generator of space-time translations. Now, this is the situation where you have n equals 1 supersymmetry. So you have one of these Weiss spinors. However, nothing prevents me from having, let's say, several of them. So let me put another index, capital A. So A now goes from 1 to an arbitrary n. This is the number of supersymmetries of the theory. Well, now the parameter of the transformation here, when you, for example, when you have this kind of object, you have these transformations. It generates transformation like this, where this is the parameter of the space-time translation. Now, these guys have, there are also things like you can add something like this. Well, now this is just a fermion, a Grassmann variable, an anti-commuting object. So this is how they act, basically, on states. And then, so if you have n equals 2 supersymmetry, it means that now this is 2. But this would be now spinors in 10 dimensions, not in 4 dimensions. And then you can try to see, once you have a spinor in 10 dimensions, this has got several components, and how it looks like from the 4-dimensional point of view. So you will see that basically one of them, I will show that one of them will become, one of them in 10D will become 4 of these in 4D. Okay, and then this, roughly speaking, how. Now, supergravity also means that this guy, this parameter, is a function of space-time coordinates. It's a local supersymmetry. Now, what do I want to say? Okay, let me first motivate why we do this. So why we want to get n equals 1? Because this theory will have n equals 1 supersymmetry. This theory, I mean, type 2B string theory compactified on a Calabi-Yau threefold with an orientifold involution, an orientifold projection. At the Kaluza-Klein scale, this will have n equals 1 supersymmetry. Now, the idea is that you use this supersymmetry to constrain your effective theory, and then to do phenomenology, this n equals 1 supersymmetry is broken down at low energies. Low energies, I mean, maybe not too far from the TD scale, to n equals 0. So maybe let me write it down. So, because there are other compactifications where you break supersymmetry completely. For example, if you compactify on a 6-dimensional sphere, you would get, we'll see that you get n equals 0 supersymmetry. Can I put it here? Yes. So the reason, so let's say we focus on string compactifications which lead to n equals 1 SUSY in 4D for several reasons. Let's say, since 1, n equals 1 SUSY gives control over the effective field theory. Because you have seen, if you have seen some of these supersymmetry in your courses, you've seen that supersymmetry is a symmetry that constrains the form of your quantum field theory. So it's a quantum field theory, it's an ordinary quantum field theory with extra symmetries, which means that corrections beyond 3 level are constrained. So they can have only a certain form. So for example, the effective field theory is written down in terms of 3 main functions. Maybe you've seen them or you heard about them. So the superpotential, the Kähler potential, and the gauge kinetic function. Did you? Yes? Everyone? Yeah? Okay. So basically what happens is that due to non-renormalization theorems, which basically tell you that the superpotential does not get corrected at any order in perturbation theory. So, for example, W, the superpotential W, receives only non-perturbative corrections. So because of that, it's simpler to write down the effective field theory and to have control over corrections. Because in general, doing this, it's very easy in words, but in practice, to compute the effective field theory with all possible corrections is very hard. And having some protection from supersymmetry is pretty good. The second point is that n equals 1 SUSY is chiral. So chiral means that you see here, once you build the super Poincare algebra, then you need to look at the multiplets, the supersymmetric multiplets, as you have for Poincare. And these get bigger and bigger, right? When you have supersymmetry. And when you increase the number of supersymmetries, these super multiplets get bigger and bigger and bigger, up to a point which is already there with n equals 2, that these multiplets are not chiral anymore, in the sense that you have left and right Weyl spinors in the same supersymmetric multiplet. However, this is not true for n equals 1. So for n equals 1, there is a superfield, supermultiplet, which is called the chiral supermultiplet, where you only have left-handed Weyl spinors, for example, without right-handed Weyl spinor. So this theory can distinguish left from right, which is what we see in the standard model. So the standard model, weak interactions distinguish left from right. And so this is due to get the standard model. So in a theory which is n equals 1, so can get the standard model. And the third point is that n equals 1 SUSY now should be broken spontaneously now. So within this 4-dimensional effective field theory, which is supersymmetric, one should study the breaking of supersymmetry, and one can study at which energy scale this remaining n equals 1 supersymmetry should be broken, which would tell us at which energy scale we should see, for example, the supersymmetric partners of the standard model particles. So spontaneously broken at low energies I mean, we don't know where supersymmetric particles lie at the moment, so they do not need to be a low energy, okay? But maybe you've seen in the supersymmetry courses that low energy supersymmetry, with low energy I mean supersymmetry that is not that far from the TV scale, has got a lot of good features. For example, to address the hierarchy problem for the Higgs mass, for dark matter, for gauge coupling unification, for explaining electroweak symmetry breaking via radiative corrections, via loops, and so on. So, for example, via a dynamical mechanism, so let's say to recover the good properties of low energy SUSY. Of low energy SUSY, which means, as I just said, hierarchy problem, dark matter, gauge gap unification, and so on. On top of that, let me put the fourth up here. Why not using this blackboard? So the fourth is that in this kind of framework, the breaking of supersymmetry of this remaining n=1 supersymmetry can take place naturally by some fields here, some scalar fields which develop some vacuum expectation values different from zero. Is a kind of Higgs mechanism somehow, and they interact gravitationally with the standard model, and they mediate the breaking of supersymmetry to the standard model, generating masses for the supersymmetric partners of the standard model fields. And the way that supersymmetry is broken is softly. So softly means that basically you give a mass to the selectron, let's say the partner of the electron, which is higher than the mass of the electron, but the couplings remain the same. And this guarantees the cancellation of quadratic divergences, for example, to the Higgs mass. And this soft breaking takes place naturally within this effective supergravity theory. Soft terms for Gauginos, so these are the supersymmetric partners of the gauge bosons, and squarks and leptons. So these are scalar particles which are supersymmetric partners of leptons and quarks, are generated naturally in this setup. Let's say in supergravity, SUGRA, via gravitational interactions. The Gauginos, yes. So they are, because you see that when you have a boson, the supersymmetric partner is a fermion. So these are supersymmetric partners of particles with spin 1. So they are spin 1 off. And what was I going to say? Yeah, for example, here, by the way, a way to get these soft terms, which are not that far from the TV scale, is if you break supersymmetry low energies. And this can be done, for example, by using non-perturbative effects. So non-perturbative effects are small because they are exponentially suppressed in terms of some couplings. And so they can explain why, starting from some scales which are very high, well, we know that this is 10 to the 18 GeV. As I said, we don't know what these are. This is something that we need to predict depending on the string of the volume, but these are also not expected to be too low. So let's say, I don't know, just to give you some numbers, this could be 10 to the 16 GeV, this could be 10 to the 15 GeV, and you want to go down to the TeV scale, which is down here. Let's say the energy of the LHC, let's say at around 1 TeV, and non-perturbative effects can explain with this non-perturbative exponential suppression why you break supersymmetry at a low scale. Okay. Are there questions on this general picture? And by the way, here there will be a lot of scalar fields. So we have already seen one example, which is phi, the dilaton. These will also be, so here in this expression, this should be thought of as the vacuum expectation value of a field, again, in 4 dimensions. These are all scalar fields. And given that we want to look at the end at applications in cosmology, maybe you have seen in some cosmology lectures that inflation in its simplest realization needs a scalar field, right? The scalar field with a very flat potential. So any of these fields, in principle, could be a good inflaton candidate. So a good field that can explain why the universe inflated, okay, at the beginning. And okay, let's now let's see, because I had thought about longer notes, but let me skip a few things. So this is the general picture. So let me also say that historically, just to give you an idea, this is not how people started to try to connect string theory to phenomenology, because this was in the mid 80s, and people did not consider type 2B at that time, but they started with the heterotic string because of this reason. So let's look at the massless spectra. So with massless, I mean here. So when we are here in 10D, so we are at energies below the string scale, so we don't see the heavy string states. We only see the massless string states. And so you have so type 2 B, and write type 2B. So I hope you have seen in the preschool that there are, I mean, once you consider closed strings, when you go around the string, there are boundary conditions. And then you can have bosons that go back to themselves. And these are NS, Neveu-Schwarz conditions. But when you have fermions in the superstring, you only have fermionic bilinears, which give you observables, as in standard quantum field theory. So which means that on top of periodic, you can have also anti-periodic boundary conditions. And these are the Ramond ones. And then you have different sectors of the theory because you have left movers and right movers. You've seen that. Very good. And so you can have an S, Ramond, NS, Ramond, and S for left and right movers. And so here, basically, you get the states which were there also in the bosonic string. So you get the metric in 10D. Now, when I use these capital indices, so M and N go from 0, 1 to 9. Then you have an anti-symmetric the Cabra-Ramond field. So an antisymmetric tensor, B, Mn, a two form, if you've seen forms. And then you have the dilaton, phi, that guy over there. Now in the Ramond-Ramond sector, the fermions give space-time, when they pair up, they give space-time bosons. So there is C0, so this is also scalar, a zero form. Then there is another antisymmetric tensor with two indices, a two form, C2. And there is another one that is C4, so an object with 4 indices. And here you have instead fermions. So you have two gravitini, psi m1 and psi m2. So these are Rarita-Schwinger fields, so spin triads field. So they have an index m, a vectorial index. They have also a spinorial index that I'm not writing. Let's say like alpha that I wrote down before. And the theory is n equals 2. So there are two gravitinos. There are always as many gravitinos as the number of supersymmetry. And now these guys have chirality as spinors, which is plus, so the same chirality. And then you have also dilatinos, so lambda -1 and lambda -2. Now, the point with type 2b, you see that if you want to get the standard model, which is something that we know that should be there in 4D, one thing that you should get in the standard model are non-abelian gauge bosons, right? Non-abelian gauge bosons. However, here, basically, you can look at the fact that there is no way in this theory to get from the closed strings non-abelian gauge bosons that look like the ones of the standard model. Because here you have a metric. If you've done some Kaluza-Klein theory, you see that maybe from a metric, when you go from 10 dimensions down to 4 dimensions, you can get a metric in 4 dimensions. Then, have you seen it? No? Okay, we've seen it, but maybe in the afternoon, you can get vectors and scalars. But this is a kind of object that with two indices. So when you want to get vectors in 4D, let's say that I have mu that go from 0 to 3, and mn go from 4 to 9. So these are the extra dimensions indices, and these are the standard Minkowski indices. I could have something like G mu m. Okay, so from the point of view of 4 dimensions, is an object with a vector index. However, you have basically to reduce these on something that is a one cycle in the extra dimensions, but in the Calabi-Yau, in the case of Calabi-Yaus, you don't have them. So it is just a property of Calabi-Yaus. And the same is true for this guy. So you don't get vectors from them. There is a possibility here from this guy, C4. So that's an object with 4 indices. So you could get, in theory, something like C mu m and p, something like this that has got one index here that looks like a vector in 4D. And in fact, you do get these guys. These are U1. So these are abelian gauge bosons. They are non-abelian. But on top of that, they also couple just to branes. so to heavy states, so they do not couple to any massless degree of freedom, so they're not good for the standard model. That's the reason why at the beginning people were not interested in type 2b, whereas people were looking at more at heterotic compactifications, because in the heterotic, sorry, what time should I finish? At 10:15? Okay. So, whereas in the heterotic, so the heterotic theorem, when you look at bosons, so you have G, Mn, you have the metric, you have B2, you have phi, but then there are also A, M, little a. So these are non-abelian gauge bosons in 10D. Maybe you've seen that. Now these guys can give rise to some non-abelian gauge bosons in 4D. Okay, so that's the reason why people started looking at this theorem at the beginning. However, and there are still a lot of people working on it today. I want to keep this. There is a lot of work going on heterotic compactifications, but there are problems there. Let me try to very quickly describe them. So the heterotic phenomenology has issues. So the first one is that, so what happens here, so this A goes from from 1 to the dimensionality of the group, as you usually have for vectors in the adjoint representation. Now the group here, G, there are two types, is SO32. Another possibility is E8 times E8. It's a very complicated group, but it's an exceptional group. But the important thing is that this group can contain the standard model gauge group. And one can have a Higgs mechanism here with some scalars that get back in expectation values, and these can be broken down to the standard model. So one can have something like this. There is a breaking of E8 to E6. Then this can go down to SO10, which contains SU5, which contains the standard model gauge group. So there is a way to break it down to the standard model. And these are good, maybe you've seen these, these are good gauge groups for grand unified theories, for GATT theories. And in these heterotic compactifications, the coupling alpha GATT of these GATT theories, which is the coupling G squared of alpha GATT divided by 4 pi, one can check that goes like G string squared divided by the volume. And the phenomenologically relevant value is 1/25. This is a simple number to remember. But then you see that if this is the case, it's very hard to have an effective theory where G string is small and the volume is big because of this guy. So this tells me that the volume, roughly speaking, is G string squared times 25. Then if I want to trust perturbation theory, let's say G string is whatever, 0.1, let's say, the volume is 1/4. Then I don't trust the supergravity approximation. I can have higher derivative corrections. So let's say hard to trust effective field theory with small G string and big volume. I mean, there is nothing wrong with that, of course. If you can compute corrections to the effective field theory, this can work, but it's hard. On top of that, there is a second issue, which is moduli stabilization, and is the following thing. So as I said earlier, the dimensional reduction of the metric of GMN of X gives rise in 4D to many scalars. Many means really a lot. To many scalars. We will see that, so this metric has to be the metric of a Calabi-Yau, and one can see what kind of deformations one can perform of this metric in such a way that the space remains Calabi-Yau. And these deformations are parameterized by some mathematical quantities, moduli, which from the point of view of physics correspond to scalar fields. A lot of scalar fields with gravitational couplings, because they come from the metric. So the idea also here, you see that if you have the metric just intuitively, right? As I said earlier, I have GMN, right? Now, if I consider M and N, which are little m and little n, okay, which are extra dimensional indices, but now I don't see the extra dimensions anymore because I am in a 4-dimensional effective field theory. These guys do not have any index, so they behave as scalaries. So you see they are like scalar fields in 4 dimensions. And there are mainly two kinds of these fields. So the first kind, they're called Kähler moduli. So these parameterize deformations of Y6T of my extra dimensional manifold in size. So you have the volume of the extra dimensions, you can make the extra dimensions bigger or smaller, and there are some fields which take different values and parameterize the size of the extra dimensions. So an example is the volume, which is now a function of, this is x mu. Okay, so this is just a scalar field. In general, there are several of them, let's say Ti, and they are complex, and they are counted by a quantity which is called the Hodge number. And this counts the number of independent harmonic 1-1 forms that you can define on a Calabi-Yau. So this is the harmonic 1-1 forms. So if I have time in the afternoon, I will explain this a bit better. I'm not sure, let's see. The second possibility is that you can, once you have the extra dimensions, you can keep the volume, which is the same, but you can deform them in shape, right? You can change the shape. Think about a torus, right? You can shrink one cycle, make the other bigger, but remaining with the same volume. You're changing the shape. So in that case, you're changing the complex structure of the manifold, and these are called complex structure moduli. These are also scalar fields that come again from the metric, and these are deformations in shape. And these guys, let me call them U alpha, they are also counted by H12, so a different Hodge number. These are the number of independent harmonic 1, 2 forms that you can define on a Calabi-Yau. Now, the fact that so these numbers, they are with respect to holomorphic and anti-holomorphic coordinates. Maybe you know that once you have a complex space, you can give coordinates which are z and z bar, right? So any form, if the manifold is complex, so if you can give complex coordinates, so if locally looks like complex space, then ordinary forms become forms with a given number of holomorphic indices and anti-holomorphic indices. And plus, we've seen the dilaton, which actually pairs up in the supergravity effective field theory with the field C0. So this is e to the minus phi plus I C0. This is the Ramond zero form, which becomes the imaginary part of this field. The real part is e to the minus phi. So one has that the vacuum expectation value of the real part of S is 1 over G string. So these are the main fields, and in general, because of course these depend on these odd numbers, that they are different when you pick different Calabi-Yau. So each Calabi-Yau has got different values of H11 and H12, but in general, H11 of Y6D is of order 100, as well as H12 of Y6D. So this means that in the effective field theory, there is really a plethora of these scalar fields. And these, now I guess I can erase this general picture. Now these guys are 4-dimensional scalar fields which are only gravitationally coupled to ordinary matter. And you can see these intuitively because they come from the metric in 10D. So because of that, it makes sense that they are coupled only gravitationally. So moduli are uncharged. Uncharged, I mean under the standard model gauge group. 4-dimensional scalars with gravitational couplings to matter. There's nothing wrong with that, but which are massless at leading order in the supergravity effective theory. Okay. This is what happens. So when you look at the theory at 3 level, so this is what I mean with leading order. So you start from your 3-level 10-dimensional string theory, you go down to 4 dimensions. These fields are massless. And do you see any problem with that?
Yeah.
You would see all these particles.
You would see how you are able to produce them, okay, because you have enough energy. But then to see a particle, this has to interact with your detector. But they have only gravitational couplings, so they would escape detection. But there is another kind of detection still, because these guys, you see, they come from the metric, and the graviton is massless. And because of the fact that it is massless, it mediates a long-range interaction, which is gravity, right? But now there are extra fields which would mediate now fifth forces, which are long-range, because these guys have gravitational couplings and they're massless. And people test these things, and they didn't see any fifth force. So let me write it down. So this is a pheno disaster, let's say, for two reasons. One is the one that I just mentioned. So these guys would mediate, so they would mediate Yukawa-like, right? Because these are scalars. So Yukawa-like long range, because they are massless, long range fifth forces. Fifth forces which are not observed. So let's say that you have something like this. I have a Lagrangian in 4D which contains a term like a Yukawa interaction. I have some phi bar psi, okay? Well, now these are standard model fermions, and phi is one of these guys, one of these moduli. Now, this is gravitational, so it's an interaction that has to go like 1 over m Planck, okay? Just by dimensional analysis, here there has to be a scale which is a mass squared, mass cubed. Mass squared, right? Because this guy here is dimension 3, right? We need to get dimension 4, so this should go like a mass, so a mass squared. The only mass here, you can have the mass of psi, so this is what you get. But then you see that you will get some kind of interaction like this between psi mediated by phi. This will be the fifth force that we don't see. These couplings are 1 over m Planck here, 1 over m Planck here with the mass. And actually there are bounds on that, and the bounds are the following. So the mass of the moduli should be bigger than something of order 1 millielectron volts. So these are present bounds. If they couple as 1 over m Planck, as they do in general, so if you manage to give them a mass which is larger than millielectron volts, then this will become short range, and then it's fine. This will be compatible. But at 3 level, they are massless. So which means that one has to add corrections to the effective field theory and see if these corrections beyond the leading order develop a mass, which in general is a hard task. The second problem is a lack of predictability of the effective field theory. So because in string theory, there is only one parameter which is the string length, if you want, alpha prime, or the string scale, and everything else is derived from it as the vacuum expectation value of these fields. For example, we have seen before the Planck scale, the relation between the Planck scale and the string scale. So you can see the Planck scale derived from the string scale, and the Kaluza-Klein scale as well. But this is true for all the features of the effective field theory. So if you don't know what these guys are, you don't know anything predictability. You don't know anything about the effective field theory. Because if they are massless, it means that if I draw the potential for these fields, V as a function of phi at 3 level, so this would look like what? Very good. So this will be flat. So these are flat directions, right? The mass is the second derivative of the potential. So the potential is a constant and the mass is 0. So this means that this field will experience huge quantum fluctuations if it remains massless. So I don't know where the field sits. So if I don't know where the field sits, I cannot make any prediction. So let's say all features of effective field theory, of 4-dimensional effective field theory, should be determined dynamically by the vacuum expectation value, is what I mean with VEV, vacuum expectation value of a modulus of all the moduli in general, phi. And this is true, for example, for the gauge coupling. So the Young-Mills gauge couplings are functions of the moduli, which I am now collectively denoting as phi. So phi now is all the Kähler moduli or the complex structure moduli, the axiodilaton. There can be also other fields related to open strings, but let me now ignore them. So the coupling of the Young-Mills theory depends on phi. The Yukawa couplings as well, Yijk, these are functions of phi. The gauge group itself is a function of phi. The masses of the supersymmetric particles, the masses of the moduli themselves, so the mass spectrum in general is a function of phi. The SUSY breaking scale, so the scale of supersymmetry breaking, is a function of phi. We've seen that the string scale is a function of phi. The Kaluza-Klein scale is a function of phi. The cosmological constant is a function of phi, and so on. So if you don't know what is phi, or even the scale of inflation, given that we want to do some cosmology, so h, the Hubble constant during inflation, is a function of phi. So if you don't know anything about phi, you cannot predict anything about your effective field theory. So what you have to do, you need to introduce a potential. So you need to introduce a potential by including corrections beyond the leading order. So need to introduce effects, corrections, so effects beyond the 3 level or beyond leading order, to generate a potential, for the moduli, for phi. And this potential should have a stable minimum. That's important because I can have a runaway, for example. So I develop a potential, but this is not fixing the value of phi. It is just giving a rolling solution, which can be dangerous. For example, if this is the volume, I can go to infinitely large values that would decompactify the theory. So it should have a stable minimum. And the problem that addresses this is moduli stabilization. This is what I meant with moduli stabilization. So one has to study effects that develop a potential which somewhere has got a stable minimum for phi, and this is where you expect the end phi to be. Okay, so this would fix it, would stabilize it to some value, and then you can make predictions. So you can read off all these scales as a function of phi, and by looking at oscillations around this minimum, by expanding the theory, you can compute the mass of the moduli. You can compute the mass of phi. So you should be in a situation where you develop this potential. Now this is different from zero. It has got a minimum somewhere. There is a minimum, and when you look at the Hessian, this is positive definite. The eigenvalues of this one give the mass squares, right? So the eigenvalues give mi squared for all these guys, and they should be steep enough to give a mass that is at least larger than millielectron volt. That's not that bad, actually. Millielectron volt is a pretty low scale. However, there is something that now I don't have time, but maybe we will see it in the afternoon. I think it's important for cosmological applications. There is a problem that is called cosmological moduli problem that gives a bound that is actually much, much stronger than that one. I will describe this problem in the afternoon. This is the mass of phi that should be bigger than something of order 10 TD. So it's really very big. And this comes from the fact that if these guys develop a mass which is not too large, they would tend in the early universe to decay very late because they are gravitationally coupled. So they are long-lived, and if they are very light, they decay very late, and they can destroy the predictions of Big Bang nucleosynthesis. So we know that Big Bang nucleosynthesis is the theory that explains the light element abundances very well, and you don't want to have some fields which at a certain point in the early universe decay after Big Bang nucleosynthesis has started and dilute by injecting entropy into the thermal bath. They dilute the light elements, and because of that, one has this bound. So this problem is pretty severe. There are ways to solve it. This is what we'll see in the afternoon. And once you know how to do this, then you can look at cosmological applications. You can study these potentials, see, for example, how cosmologically one gets to this minimum, to this late time minimum, having, for example, a time dependence of this field, and the dynamics hopefully can, for example, describe inflation or dark energy today. I think it is a good point to stop.